In today's digital world, randomness is everywhere. It protects our password, secures our transactions, encrypts our messages, and keeps our data safe. But here's the problem: not all randomness is truly random. Some systems generate numbers that only appear random but follow hidden patterns. Once these hidden patterns are identified by attackers, they can predict the future. Once the randomness is predicted, security can be collapsed. So here's the question: how do we generate numbers that are truly unpredictable? This is where our project comes in. Today we will explore a powerful algorithm called Blum Blum Shub, which generates secure, unpredictable random bits. Let's understand the problem more clearly. Many traditional random numbers generate, like the linear congruential generator, are widely used because they are simple and fast. But they have a major weakness: they are predictable. If an attacker observes a few outputs, they can mathematically calculate the next values. This means passwords can be guessed, OTPs can be predicted, encryption can be broken, and clearly this is unacceptable in security systems. So we need a generator that is random, unpredictable, secure, and this leads us to the cryptographically secure pseudo-random generators like Blum Blum Shub. Blum Blum Shub, commonly known as BBS, is a cryptographically secure pseudo-random bit generator. It is designed using properties of numbers, especially using properties of prime numbers. What makes BBS special is that it is a mathematically hard factoring numbers. So it is very difficult to predict the future number even though the previous number is already known. It does not focus on speed, it focuses on security. Now we will see the working of the algorithm in step by step. Step 1 is choosing prime numbers. At first, we choose two large prime numbers. The numbers are not only prime, it should satisfy a special condition in which both P and Q must be congruent to 3 modulo 4. In the second step, we will calculate the value of n. Value of n is calculated by taking the product of P and Q, which is further used for taking the modulus of a number. Step 3 is choosing a seed value. Here we choose an initial value called as seed, which is denoted by x naught. It is the starting value of the sequence. Seed and n must be coprime, meaning that they both does not share a common factor. Step 4 is applying the core formula: xi plus 1 equals xi square mod n. Here, new value is generated by squaring the previous value and taking modulus of n. This makes it very difficult to predict the values. Step 5 is generating output bits. From each value generated, we generate a output bit, that is, using the formula x mod 2. If the remainder is 0, then the value generated is 0. If remainder is 1, then the value generated is 1. In this way, we generate a series of bits. It is extremely difficult to reverse and predict the future values, and this is exactly what makes Blum Blum Shub cryptographically secure. Let's go back to our previous example of OTP generation. If a system has Blum Blum Shub, even if the attacker sees the previous value, he cannot see the OTP value of next one. This makes the system more secure. So let us see the next example to understand it clearly. For demonstration, we will use small numbers. So let us take P is equal to 11, Q is equal to 19, C will be equal to 3, and N equal to 209. So we'll solve this using step by step. So for the first iteration, we will square 3 with mod 209 will be equal to 9. And for the second iteration, 9 will be squared and we will use mod with 209 will be equal to 81. And for the third iteration, 81 squared mod 209 will be equal to 82. For each particular iteration, there will be a particular bits. For example, for the first iteration, the bit will be equal to 1. For the second iteration, the bit will be equal to 1. And for the third iteration, the bit will be equal to 2. So the total bits will be 1, 1, and 0. So not only for the small numbers, we can use in real time also by using large prime numbers. With this, the system will be more secure. This function checks if the number is prime or not.
So the logic is if the number is less than 2, then it is not prime. And then we will check the divisibility of from 2 to root n. If the number is divisible, then it is not prime. If the number is not divisible, next one is valid prime condition. So the BBS requires some prime numbers such as p congruent to 3 mod 4. This function checks if the number is prime or not. When the number is divided by 4, it will give the remainder. So the next one is main BBS function. This performs the entire BBS algorithm. There will be some inputs such as P and Q are prime numbers, seed is the starting value, and N will be the number of bits. So here there are few steps. Step 1 is validate prime. Here we have to make sure P and Q are prime and it satisfied mod 4 condition. If not, then the program will stop. And the second step is we have to compute n. For that, P and Q are multiplied and it is used for mod condition. The third step is to check seed. So the number must be co-prime with n, which means GCD of seed comma n is equal to 1. So the next step is ensure variables. Uh, the x will store the current value and bits means it will store the output values. So the next step is core logic. Here we have to square the numbers, then take modulus. After that, then the values will be within the range. Then generate bit. If even, then we have to take 0 as value. Or if odd, then we have to take 1. And then we will store the result. After that, the bits will be append to the list. This will generate pseudo-random value. Now let's compare BBS and LCG. LCG is fast and simple but predictable. BBS is slow but highly secure. BBS is suitable for encryption, key generation, and secure communication, while LCG is suitable for stimulation and non security application. Conclusion: Blum Blum Shub provides a strong solution to the problem predicted randomness. It ensures that generated numbers are highly secure and different to predict. Although slower, it is ideal for application where security is critical. This makes it is a powerful tool in modern cryptography.